So now I'm going to talk about a few of the other types of traps that we're building. And incidentally, that the gallium arsenide trap was I looked at my prelim before giving this talk, and in my prelim I have all these pictures showing the gallium arsenide trap, but it was before it worked, and we were able to trap a few months after that. And since that time, other groups have gotten interested in actually doing the semiconductor fabrication of these traps. And so a couple of foundries have started where they actually build the traps and then send them to us to test. One of those is the polysilicon MEMS trap, and that's very similar to the two-layered structure of the gallium arsenide trap, with the following differences. The conducting electrodes are made out of doped polysilicon, and the insulating layer is an air gap, and that is really nice for two reasons. One, the voltage breakdown between these two we hope will be much higher than in the gallium arsenide trap. And also the capacitance between these two layers will be about a factor of 5 lower than what the gallium arsenide trap was.
Will there be some sort of mechanical stabilization so that
Well, for the gallium arsenide cantilevers, we measured their, or we estimated that their resonant frequencies would be between about, half a megahertz to, 100 kilohertz to 10 megahertz. Now that sounds really bad because it's in the region of the secular frequency. However, the Qs for those resonators are in the thousands. So to be able to, it shouldn't be a problem unless you're right on resonance with your secular frequency.
The thermal excitation
doesn't broaden that?
No. So one way is exactly what's some random noise source
at say 1 megahertz or 2 megahertz?
Yeah, you always have thermal excitation, right? There's random noise sources. I don't know.
I mean, so another possible source of excitation would be the fluctuating RF fields, but since those are much higher than the secular frequencies.
Yeah, so that was really my concern. But here on this one, I have a much longer standing structure, so the resonance frequency is lower, right? And here to excite, right? So we will not directly coupled to the ion, but if you imagine your cantilever oscillating with a high amplitude, it can be good, right?
Right.
So I'm just wondering whether the key is doing some mechanical stabilization structures with some vibrating at high amplitude.
So these structures are, probably actually the previous picture was better for seeing it. The only stabilization in these are you have your bottom layer, which consists of a rectangular electrode that then has this little bond pad out here. The top cantilever has a cutout region right there so that you can actually access the bottom electrode. So its stabilization is way back here where the bond pad is. So I mean, this was a concern for us in the gallium arsenide trap, and in fact we had speculated that maybe its mechanical resonance led to its high heating rate, and we tried to measure that by making an interferometer and bouncing a laser off the electrode and looking for and scanning to see where that resonance was, but we never saw anything that was any prominent features in that.
What's the length, the lateral length?
Like this?
Yeah.
So these, I should mention, these traps are being made for us by MEMS Exchange. And they're making a variety of traps, but the characteristic length is on the order of 500 microns. So from here to here.
And the thickness is?
The thickness of the polysilicon is 0.75 microns.
And it reminds me of the AFM test, which is sort of lightweight, and people use that vibration
Right.
as the way to monitor what's
But
going
now
on.
those have like a really thick substance under them, right? I just
No,
think
it's
I
not,
don't know
it's
exactly.
not, it's not that different from, so that if you want to look at that top orange thing, it is not that different from a cantilever.
Oh, yeah, it's identical to a cantilever.
So do you have an estimate of how much it would be wiggling around?
Well, most of our measurements are for the gallium arsenide, and in that case, we estimated that the motion of the tip was on the order of 10 nanometers. So,
Complicated ion motion is also very high speed.
so unless this oscillation frequency
It's not
is
regular,
exactly at where
then
the
you're
ion,
okay.
then we're okay. So this is an overhead picture of that trap. Another type of trap that we've tried, and this I haven't mentioned this sort of design before, is the surface trap. That work is being headed by Dick Slusher, who was at Houston and is now at Georgia Tech Research Institute. And that consists of, in this transverse picture, of these RF rails that are suspended 10 microns above the surface with silicon oxide. And then you have DC electrodes, those are these gold electrodes right here. And you can visualize this as kind of like railroad tracks. So in this overhead picture, you have the RF rails like that, and you have all your DC electrodes. And you can't see the gaps in between them because they're only, I think, 2 microns, but otherwise you would be able to see a gap right there, and there, and there, and so on. And so in this type of trap, you get an RF node, which is about 50 microns off the surface, depending on the separation of these 2 RF rails. And it has a few nice features to it. One is that it's relatively easy to fabricate. Well, maybe that's probably not, that depends on